Here I will introduce a zone theorem. So the setup is the following. We have a set of M lines in this picture. Then I have a line L that is just an arbitrary line. The zone of this line is the set of all the cells intersected by this line L. So this is all the cells intersect by line L, and this picture these are highlighted. And the complexity of the zone is the total number of edges on all these faces. I will have to reiterate this. Remember that the number of faces is M, but what we're counting is the total number of edges of those faces. So for example, if I have face 1, face 2, face 3, all the way up to face M, or I guess M plus 1, I add the number of edges of all these faces up to make up the complexity of line L. In other words, I look at this face, I count all these edges. So here 1, 2, 3 edges, 3 plus 4 plus 4 plus 4 plus I guess 1, 2, 3, 4, 5, 6, 7, I guess plus 7, etc. You add up the complexity of all these faces, and that number at the end is the complexity of the zone of this line L. When we go to the previous algorithm, we can clearly see that the running time of the ith iteration is at most the zone of line Li. This is because at every step we can walk through all the edges of a cell to find this exit. So the amount of work that we do is proportional to the complexity of the zone of this line Li. And if we can prove that the zone of any line has linear complexity, then it follows that the previous algorithm runs in n squared time, because every iteration of the for loop will run in linear time. This theorem is a very deep theorem because the obvious bound that we can get is m squared. For example, when I look at this picture where I have m lines that go around one cell, the complexity of this red cell is already m, even though the line L intersects a whole bunch of cells to the right and to the left. But even though one cell could have m complexity, what we want to prove here is that all the other m cells in total will have still O of m complexity. And in other words, what this theorem says, you cannot have too many of these cells, highly complex cells, in a row that can be intersected by the same line. This is a theorem that it belongs to a branch of mathematics called discrete mathematics. This type of discrete results, they're not algorithmic results. This theorem, it's basically about the structure of a set of lines. It has no algorithmic aspect to it, but it is vital for us because we can analyze an algorithm using this theorem. And these type of theorems are very important when it comes to higher understanding of algorithms and when it comes to designing better and more efficient algorithms. In the next video, we're going to look at the proof of this theorem.